Thank you very much for the very kind introduction. And hello, everyone. So just a little background, so that we are basically on the same terminology and wording for this talk. So a blockchain is a chain of blocks. Right? That's where the name stems from. Typically, a block has a so-called link to the previous block. That's why it's a chain. And there's a hash, a cryptographic hash, which is like a fingerprint. There's also a list of transactions included in those blocks. And this is kind of what is committed to the chain. Right? So if a transaction is in the chain, then you can use it. It's validated. Miners are the ones doing or creating those blocks, and these miners can be proof of work miners, but they could be also other types of miners or validators. Right? It's just a general term. Why would they do this? So in the proof of work setting, they are calculating a puzzle, right, which is computationally intensive, and in order to find the next block B2, they have to find the hash of a block B2, which is smaller than a given threshold. That's a challenge that is resolved in a global decentralized network in the case of proof of work, but there are others, as we will see in a bit. So why would a miner do this? I mean, this is a lot of work. It's expensive. Well, they do get a block reward. And in an open and permissionless setting, you get a block reward. In a permission blockchains where there are individual participants, they would get the power to vote to be in this consortium. So once a block is found, it's distributed, and this distribution typically happens over a peer-to-peer network. It needs to be communicated with other participants, right? And this communication is slow. The world is big, latencies are high among different continents, and that's one of the major bottlenecks, as we will see in a bit. So once this block is found, it's appended to the next, to the previous block, and it could be that a competing miner finds another block at the same time, and ultimately only one of these blocks can remain in the main chain. Blocks that are discarded are called stale or orphan blocks. So this is a typical blockchain structure. There might be other structures like tree structures or directed acyclic graphs, as you might have heard. But that's typically how we reference a blockchain. Okay, so this was enough background on the technical part. Now on the network part, what's important to understand in order to understand blockchain scalability is that if a miner or validator finds a block, it takes some time to propagate. And during this time, it could be that another miner or another validator finds another block, right? So you have this conflict here and kind of a partition in the network that divides the network into two parts, where some are working on one version or one history, or you can call it one reality, and the other on the other. So these stale blocks, they're, at least in proof-of-work blockchains, they are lost efforts. So lost efforts in the sense that they're basically two parties fighting against each other, right? And if two people are fighting, well, a third person is benefiting. So an adversary has an easier game if two people are fighting here. And this is not theory, this is reality. So I'm just plotting here some stale block rates for open and decentralized blockchains that are based on proof of work. Okay, so how can we see that blockchains don't scale? Well, we see it, for example, in Bitcoin. There are the number of unconfirmed transactions here that you can see. This was in January this year. And these are the transaction costs, the fees for the transactions. So no sane business wants to run an application where the transaction fee go from below $10 to over $50 within the matter of a few weeks. Right? That's just not sustainable. I mean, you don't have a service level agreement. Although it's always up, you can never really be sure how much it's going to cost. So that's a big risk for businesses nowadays. So in order to understand the blockchain scalability, we also need to take a step back and think of the different layers. So there's the hardware layer where we're processing blocks, we're validating transactions, we're computing signatures. There's the network layer where we propagate information. There's the blockchain layer where we actually form the consensus, the blockchain. And there might be other layers on top of it, which can be application layer. There could be other blockchains. And this is typically where we see nowadays opportunities to build bridges between different blockchains. What's also important to understand, if we're talking about scalability, an adversary can actually be on all layers here. So an adversary can always attack. And ultimately, blockchains are about security. They are about trust assumptions, and they are about moving the trust from a central entity to a decentralized network. And that's why we always need to look back. Is this still a secure, decentralized network? So what are the different scaling directions that we can see nowadays? These are some of the possibilities. So I would like to start with the network layer. So in the network layer, if we have a faster internet, if we do have more professionally hosted nodes, like validators and miners, and they are very well connected, and they use a very efficient propagation protocol, then we can probably already scale by 10 to 15-fold the throughput of current blockchains. And that would be not bad. It would be rather cheap and easy, right? There you won't fix or change anything in the trust assumptions. You simply make the base layer faster. So the second possibility would be to look at alternatives to proof of work. So there's this nice infographic from Blockchain 101 that was shared, and it lists basically different consensus algorithms. I find it very hard to compare them. The reason is that they are fundamentally different in the trust assumptions, right? Fundamentally. So proof of work, for example, is an open, decentralized protocol. 50% of the majority can take over a chain. And if you look at BFT protocols, Byzantine fault-tolerant protocols, they're typically the majority that can take over. They're secure until 33%, and they're not open. So you have to predefine the set of people that are in this network. So that makes them very difficult to compare. Some of these protocols, like proof of importance, are also unclear to be secure. There are no proper security analysis of those. So every time you're discussing a consensus algorithm with your peers, think about, is this actually secure? Has this been formally verified to be secure? Very important. Otherwise, there's no basically sense to compare them, right? And comparing all of them is a big work. In my PhD, I compared different proof of work algorithms, or like parameters for blockchains for their scalability. And this alone took like almost a PhD. So think about comparing all of them. It will take a lot of time. Okay, then partitioning is the third topic. So again, here we have a network of different peers. If you look at this network, well, I saw you earlier, if you propagate a block, it takes time, right? But what if you actually create partitions? So now we have 4 partitions here. And these partitions, they could communicate with each other, right? They can, individually, they can reach faster consensus within the partition and then communicate with the other partitions if they need so, but not for every transaction. It's, however, hard, I believe, to create proper partitions that make sense and that optimize the communication overhead. So the fourth topic I would like to go into is today's off-chain. So this is on the second layer, so on top of the blockchain layer. And in off-chain payments or computation, there are different directions that we see nowadays, different architectures that are being worked on. The first is two-party payment channels. So in two-party payment channels, you have different settings. They can be unidirectional, bidirectional. They can be linked. You can build a hub, so well-connected node, and you can build n-party hubs, so n-party off-chain hubs. So these are more, they're fundamentally different from the architecture. They're more temporal-based, whereas the payment channels, we will go into detail now. So a payment channel is a construct that has 3 phases. You create it, then it's living, and then you close it. 3 phases. In order to create it, you need to deposit some collateral. So for example, in this case, it's Ether. Okay? So each party does an on-chain transaction to open the channel. And once this is done, so the channel is initialized, you can do an off-chain transfer, which is up to the amount of collateral that you collateralized. Why up to the amount? Because you want to operate trustlessly. Okay? It's like you charge a prepaid card, and then you use what you have on your prepaid card. It's literally like this. And then one peer here can trust you that you can send up to 1 Ether because you have collateralized 1 Ether. So once you update now your off-chain balance, the off-chain balance needs to be maintained between those two participants. So if the right peer now sends another transaction to left peer, the off-chain balance needs to be erased and updated. Very important. If you don't kind of invalidate the previous balance, an adversary can use the previous balance to double spend coins that have been spent off-chain. Okay? Here we are back to security. Okay, so payment channels are great, and they're pushing the scalability of nowadays blockchains, at least the open blockchains, but they do have some drawbacks too. So if we have two peers that are not directly connected through a payment channel, you need to route a payment across a set of nodes, and each node here needs to have collateral, right, on every edge, and that's quite expensive. And you need to provide services for other people. It's not like a BitTorrent peer-to-peer network where you don't care if a node is online or not. It's much more complex. There's collateral involved, there's latency involved for payments. So if you're routing a payment and, for example, one channel here is not fully funded, there's not sufficient collateral for your payment, you need to find another route. Another route means you have to have a good algorithm to find a route. Everybody that does internet routing knows BGP and OSPFs are complicated. This peer is probably nice, but it will request a fee, right, to forward the payment. So the longer routes, the more expensive the payments, the less likely that the payment actually succeeds. But ultimately it works, and there are great teams working on different payment channel architectures nowadays. So what's I believe very interesting for many applications is our well-connected nodes, and we can see this also nowadays in payment channel architectures. There's this emergence of very well-connected nodes, or we can call them hubs, and they're good because they're very efficient. They are more centralized, but they're untrusted. Okay? So I believe we can explore a lot, especially in the blockchain space, this notion of centralized but untrusted. It's the same if you have like an open public blockchain that is kind of the main blockchain, and you have like one permission blockchain and you have a bridge between them, then this permission blockchain is kind of a specialized version, right? You still, it might be more centralized, but maybe still untrusted depending on how you set it up. So in payment channels, if you build such a hub, the central node here needs to collateralize quite a substantial amount of funds in order to provide service to its customers. So for example, if we have 1 million users and each user gets from this node about $10,000 of transaction volume per month, then you need 10 billion lockup per month in order to operate trustlessly, which is a fair amount of money. And in addition to this, for 1 million users, you need 1 million on-chain transactions, which in itself already is quite substantial. So I've been doing some research in order to improve the scalability of payment channels. So Revive is, for example, a protocol that we proposed last year. So if you do have a cycle in such a network, then let's assume we have the following collateral distribution. This node here, the left node, cannot send any funds directly to the right node. It would need to go over the more expensive route. But what if we rebalance the channel in an off-chain manner? So you can use some of your collateral here and rebalance it to the other channels, and then suddenly you can make cheaper payments. So this is just a simple improvement proposal. I mean, there's some complexities behind that I'm abstracting away here. But there's a lot of research going on, and many teams, academic teams, are working on improving scalability of payment channels. This is open source on GitHub. Off-chain hubs, there are several projects working on so-called off-chain hubs that are different from payment channels. So in off-chain hub, typically you have a periodic settlement on-chain, like a checkpoint interval. And that's different to traditional payment channels where you have open, living, closing phase. So here you have more ongoing liveness. And what's interesting is that here a new user could register off-chain, then receive off-chain transfers or transactions, and also forward off-chain transactions. So it's a more dynamic environment. So the comparison, for example, if you want to build a two-party payment channel hub, then you have to collateralize a lot. The collateral is managed for each individual link, so it's quite complicated. And also, it's tied to a particular user. You cannot use it for others. Whereas in such an off-chain hub, typically you can manage this in bulk. That's possible. The collateral requirement, as we have seen in such a hub, would be substantial if we have many users and a lot of transaction throughput. In an off-chain hub, this is typically lower. It depends basically on your checkpoint interval. The smaller the checkpoint interval, the less collateral you need for trustless operation. And we always have to come back to the question: are we in an operation? I mean, are we operating trustlessly? Right? Are we no longer custodian? Are we maybe centralized but untrusted? So the second layer is promising. It seems to be usable. Many teams are working on it. It allows instant transactions. The costs of performing such constructs are relatively cheap. So I'm running, for example, a payment hub, and the current costs of running this is like less than $100 per month, and irrespective of the number of users. So you can have zero cost transactions nowadays on the blockchain, and that's ready. So there are some, I think the second layer is very promising in my mind. Let's look at permission blockchains. So in permission blockchains, we kind of change who we trust, right? So we're introducing, for example, a consortium of a few companies or a few entities, a few governments that we do trust. And that's totally fine. And most businesses nowadays are working also that way, right? Without trust, you almost cannot do business. So typically what these consortium members do, they say, good, we agree that we're all validators now, right? They sign a legal document and explains we're willing to do this. And then they run some of these consensus algorithms that we looked at earlier. So for example, in this setting, you can obviously use proof of authority because you know the set of validators that are here, and this is much more efficient than the permissionless setting. And for many use cases, it might be very, very relevant. So just a small comparison of permissionless versus permissioned. So in permissionless, you trust typically in an open algorithm. You trust that it's not easy for a single entity to become the dominant player. So basically, you trust that the algorithm is not cheatable. Whereas in a permission setting, you typically trust in a consortium. In a permissionless setting, these are inefficient because they're open. Anybody can join and leave at any time. So it's a kind of a freedom that you get. But this makes them inefficient, right? And in a permission setting, these are typically efficient because the consensus algorithms have been worked like 40 years before Bitcoin. So there's a lot of research work. I mean, there are papers there called the 700 BFT protocol, I believe. So there's really a lot of work, much more than in the blockchain world. Permissionless blockchains are not yet privacy preserving, so everything you do on an open permissionless blockchain is public, and you should consider it public. So I wouldn't do anything criminal on them because it will haunt you in a few years' time. In permissioned blockchains, these are typically privacy preserving because there are just less people being able to look at them, right? They're kind of restricted already network-wise, and not many people can read them. It's a different setting, and that's obviously better for privacy. I believe there's much research going into privacy. It would be great to find actually, proper privacy-preserving blockchains. I mean, Zcash, Monero are just a few to mention, and I think this is just the beginning that we see. I always want you to stay vigilant. Do you actually need a blockchain? And it's good to reflect on this. It's not always the best technology for your use case, but it does have very interesting properties for many use cases. So thank you very much for your attention. Happy to take any questions.
So thank you very much, Arthur. This was great, a great presentation. Thank you very much for that. So we are going to go through a little discussion here together, of course, answer the questions from the audience. But first, I have a question. So we have seen here a lot of different approaches to scalability, a lot of different solutions that are out there. But my question would be, what is being researched, what is being used, what is already in production in large scale? So could you give us maybe a sense of what is the current state of scalability?
Yes, so I believe the easiest would be to improve the internet connectivity. I'm trying to scroll back here, this takes a bit of time. So the easiest part would be to basically improve the network layer, right? Here, okay. So this one is probably the easiest. So I've done a bit of research on my side and found some vulnerabilities in the propagation protocol of Bitcoin, which made then this more efficient. So I did a little bit of research, and the Bitcoin developers immediately implemented kind of the more efficient way. So this is an easy one. In consensus, alternatives to proof of work, there's enormous amount of work being done. I would say, yes, I don't think there are any, well, delegated proof of stake is being used quite a lot, but I see it's still, I don't want to say anything wrong, but there's some systems that I saw are more centralized because there's a central node that does checkpoints. And as soon as you have like a central node that does checkpoints, it's kind of, back to a centralized system. Sharding, I believe, is not as close as offchain, for example. So probably you asked from what is the closest to production. I would say network and offchain are the closest. Then consensus and then sharding, probably, from my feeling now. Off the chain is actually already in production. So on the Ethereum you can do this. Lightning Network you've heard, I guess, also. Yeah, I would say this is currently roughly the state of the art.
Okay, thank you very much, Arthur. Thank you again. I'm sure you have a lot of questions here in the audience to Arthur. Please let us know, and I will be going around handing over microphones. Sure.
Regarding scalability, you have described scalability for trustless networks. But in the permission networks, I feel there are not enough efforts to look at the scaling permission networks so you can create huge permission networks. Or what is your vision on this?
What do you mean by you should have more forks in permissioned network?
Effort, more research.
Okay,
not, I have not seen a lot of effort on this thing, okay, because they are typically limited and they think, okay, we focus on performance, but not on scalability. Scalability, I mean, I want 1 million participants in our permission network.
Oh,
how do you do that?
Basically, you remain with the same issues, right? You can. So the great thing about the research that is being done on these layers here is that most of it applies to both permissionless and permissioned blockchains. The advantage in a permissioned setting is that you don't have to resort to, for example, proof of work that is quite expensive in terms of energy, but you have like a BFT algorithm that basically cuts down on the mining costs. But what's actually important is that proof of work is just a election leader, right? It basically decides who is going to be the next one that creates a block. It's just that. If you use BFT, then you say who's going to be the next one that does a block again, right? Or if you use proof of stake, it's the same. You cut down the energy costs, but you still have this dice rolling of who's going to be the next one. And once this question is answered, then you need to propagate it in the network, and this is slow. So even in a giant permissioned blockchain, you will have this issue that you will have forks, because there's some, okay, it depends a bit on your consensus algorithm, but let's say we have proof of stake, and in the BFT setting, it's different. You don't have forks, right? It's the deterministic consensus. But it's true that there's, so I haven't been working much on BFT for very large scale networks, but I mean, in a BFT protocol, there's a lot of communication going on in order to reach consensus, and it's I believe if you scale, it's probably gonna have some issues. Yeah. There are some projects. I am not sure how much they scale to how many participants. I think OmniLedger might be interesting to look at in this aspect.
Okay, thank you. I think there was a question right here.
Just following up to this question, and if you can clarify one point, because apparently I've been working with Hyperledger Fabric. So recent publications show that Hyperledger Fabric has very good transaction throughput. It managed to process thousands of transactions per second. So it's quite good when it comes to transaction processing. But the point is that it's a problem with node scalability. So it can be, as the gentleman before me was saying, it can be facing issues when it comes to more nodes into. But what I wanted to understand whether the strategy for improving scalability are the same for when you have problem with transaction scalability and when you have problem with nodes scalability. So if they are, it can be addressed in the same way. And the second question, just I take advantage of this, in the consensus scheme that has been published by Blockchain 101, one of the alternative consensus system is the directed acyclic graph. Okay, we've been now a lot of buzz around the Hedera hash graph and all the alternatives, Neo, and a number of others. That provides a kind of fundamentally different philosophy, blockless and completely different way of asynchronous. And I want to understand whether, in your opinion, this is something that we should look more attentively to instead of focusing on this sort of issues that blockchain structure have, or if hash graph and so on, they are not yet at the technological maturity needed for a large-scale implementation. So I wanted your opinion on that. Thanks.
Thank you very much.
And sorry, I'm sorry for interrupting. I'd like first maybe to help the audience before we answer this question and put some numbers behind some of the discussions that we're having, because I think it's really important not to have this discussion too qualitatively. So my perception, and tell me if you disagree, is that if I'm using a public chain of, the throughput is in the order of 100 transactions per second, but of course I'm only able to capture part of the network. So what I can use is a few transactions per second as a member of that global network. Now, when we talk about permission chains, such as permissioned Ethereum, Corda, or Hyperledger Fabric, we are typically talking about transaction throughputs that are at the low end 200 transactions per second, at the high end probably 1,000 transactions per second. So that's really the range that we are talking about. And in terms of nodes, I think most of the networks become unstable once you grow beyond 30 nodes, particularly when you talk about validating nodes. And then, of course, there are technologies that appeared recently in the market that do not provide transaction finality necessarily, but are based on tangles or other architectures and are promising tens of thousands or hundreds of transactions per second. So I think those are the orders of magnitude that we're talking about. And I guess first, do you agree with this statement? And then based on that, please answer the question.
Thank you. That's actually perfect, because quantifying is always very important. However, we always need to contrast those numbers to the trust that we put into like a few validators or not, right? That's why looking at the pure number itself isn't sufficient, but it's very important to have those numbers. I do agree the open permissionless blockchains, the layer 1, the blockchain layer doesn't go over probably 100 transactions for the whole network, which is fairly small. But if you use, for example, offchain technology, you can get to Visa level, 50,000 transactions per second. In a payment channel, well, you're literally bound by the latency and bandwidth between the two peers. In a payment hub, the same, right? So there you can really scale to Visa level. There's no inherent limitation in the protocol. Back to the permission setting. It's true that these BFT protocols, they typically don't scale to many validators, so these are the miners in a sense, but they do scale to a lot of transactions per second. Yeah. So I mean, there's a lot of research going on in this field, so it's too early to say, but I'm confident there will be advancements. One strategy which has been very popular, at least in the open space, is that you have so-called mining pools. So you pool like a few validators together, right, and then you're more efficient. So it's an easy way, but then again, you put more trusts into like one particular node, right, and then you have to check, okay, is this node doing what I actually want? Okay, and your second question was about, can you quickly remind me? Oh, right, DEX, exactly. So DEX, I think we have them here, yeah. So it's I think the first protocol was Ghost that I saw on DEX from Israel. Very, very good work. I looked at it, I even tried to implement it with a student of mine. And it's hard on the practical side to implement it because you can have a lot of vulnerabilities in a practical network. For example, like how to propagate those blocks, right? Because it's a tree structure. How to determine which block you're missing. So I think DAGs are great. They're still, I think, very much in the more theoretical, not yet too applied state. But maybe somebody has found something in the last weeks and which I'm not aware of. The space is moving fast. But when I tried it, I think I tried it 2 years back, it was still, there were quite many questions, in particular on how to propagate those blocks and how to make sure that you actually find efficiently, to build this tree efficiently. Right? I think that's the major.
Just, I don't want to make it like a discussion, but the latest paper, it's back in 2016, I think, and back to the white paper. Then they implemented the idea, which is a commercial product. So I don't know much about the actual current implementation, but I know the structure. It was about gossip, and it allowed to not make this the problem you indicated before, that you have a number of blocks that at the end they are just useless because they're being calculated too late. So you just lose the effort. Instead of pruning the chain, so you make something that allows is being not asynchronous. So it's asynchronous. Then you can make things in parallel using gossip about gossip. But I don't know. This is where my understanding stops. So this is why I made the question. I wanted to understand whether it's something that we have to look more in details, because if this DAGs hash graph proves to be efficient for transaction processing, then we are losing our time in trying to scale to up 1,000 transaction a normal blockchain architecture. This is my fundamental question here.
I mean, ultimately, you will still need to propagate those blocks, right? The more blocks you have, the more overhead you have. That's why actually Ethereum, for example, has a much bigger stale block rate than Bitcoin, because the block interval in Ethereum is 15 seconds, whereas in Bitcoin it's 10 minutes. So if you use a DAG, you will have much more overhead. Every block header has like, I don't know, Bitcoin is like 80 bytes block header, which is not negligible, right? If you run over time, because you're not getting rid of those blocks, they're gonna stay. So I was particularly excited about DAGs because also Ethereum claims to use a DAG because they have anchor blocks. So the miners get a block reward for mining a block, so it's not wasted to them in terms of monetary amount. What's however important, and this is most often overlooked, is that the anchor blocks in Ethereum do not count towards the difficulty of the main chain. So this means in the end it's just a chain. So we have to always go back to the security. From a security standpoint of view, Ethereum is a chain and not a graph. Although the anchors, so the supposedly stale blocks, they produce some rewards towards the miners. So I think so your question is, should we work in the space? Yes, definitely. I think everything is worth exploring, right? Until you hit a wall or like you really try hard. I think it's always good, and we should try. But I think DAGs are tricky, in particular regarding the complexity of propagating them. I mean, gossip protocol is good, but Bitcoin is also using a gossip protocol. Right? So I think these protocols are very well explored so far. I mean, the network propagation protocols.
Yeah, I think there was a question right here. Could you please briefly introduce yourself before name, organization, and what you do?
Yes, Alex Kampa. I'm working on a project called Secoba, but I've also been a consultant at the Commission in Luxembourg. So I just wanted to make a few remarks. I would say, first of all, when we speak about transactions, it has been understood that all transactions are not equal. Okay, people will claim lots of things, but you have an Ethereum transaction can be much more complex than a Bitcoin transaction. On the one case, it's an atomic transaction. On the other hand, in other cases, it could be a smart contract or some complexity to transaction. So it's always tricky to compare. You have to see what are we talking about. The issue I wanted to address was simply that some directions of research to reduce the overhead is to actually reduce the number of messages sent. So coming back to just what you mentioned on the DAG, on Hashgraph, I noticed you have to send messages many times, at least four times through for most nodes to actually get consensus. So it's a big overhead. There are some projects, and one of them that we're looking at actually for our own project is called Honeybadger. I don't know if you've heard of the Honeybadger.
From Andrew Miller, yeah.
From Andrew Miller. So this is leaderless. All the nodes actually, do the mining, but he focuses on reducing the amount of information sent between nodes. So every node, out of all the transactions in its queue, will actually take a random subset, a reasonably small one, and then all the nodes try to get an agreement on the next block with minimizing this amount of transactions. And these guys, using just Python, they were able to get something like, I just checked it here, about 20,000 transactions per second on a 40-node network, which is quite impressive. Okay, and that's completely leaderless, completely asynchronous, which is a nice feature. And then the last thing I'd like to say before I yield is simply you have to. What's maybe missing and what I haven't seen in the research is how many nodes do you actually need? Okay, you want performance. For that you want as few nodes as possible. You want resilience and trust. For that you want lots of nodes. But surely you don't need 10,000 nodes. And surely 5 nodes are not enough. What's the kind of ideal, the sweet spots in terms of number of nodes?
Thank you for
That's lots of questions, but
thank you for these remarks. So regarding the first thing, yeah, this is a common misconception. I mean, Bitcoin has smart contracts. It's true that Bitcoin transactions are typically not that big as Ethereum transactions, but Bitcoin script is a scripting language, so you can do smart contracts in Bitcoin. It's just, who does it? Yeah, there are a lot of geeks doing it. So if you look, for example, at the Lighthouse project from Michael Hearn, he implemented like a micro lending crowdfunding platform on top of Bitcoin, and he developed smart contracts for that. So there are some people doing it. It's true that my students, for example, at Imperial, I don't let them do it because it's a hell of it's complicated and it's very cumbersome to program in script, and that's the great added value of Ethereum, right? Having a great programming environment and easier development tools. But I believe both blockchains are in a sense equal because they have smart contract abilities. So regarding your second question, yes, Honeybadger. So I have read it. I think 2 years back. I think it's 2016. So I'm not fully up to date anymore of the content. I think it's a closed setting, right? It's BFT based. So you have the set of participants that participate are predetermined in a sense, if I'm not mistaken. Okay. I mean, you you need to change the specs, right? You need to redo the security checks and everything. Like an implementation itself wouldn't be sufficient to just make it open in a sense. Before writing code, I think it's always important to, if you change the protocol, then you need to redo the whole security analysis to objectively state whether it's actually sound. Yeah.
So I think we are going to take 2 more questions. I think there was one here, and then I would be moving to next question.
Yeah. Hi, I'm Chris from a company called Royalty Range. You mentioned the stability of a network. So if you add 30 nodes, so the stability goes down. And we're actually, we have a running application based on Hyperledger Fabric. And we do hear these things that if you scale, the stability goes down. We had some issues with that. We're not sure where it comes from. And so the question is, that stability, is it due to the computing power, bandwidth, or is it a protocol? And also, I attended a number of events in the US and Silicon Valley, and there was a lot of discussions around the nano computers, so the next generation, and does it have any connection? So what's in your view the real issue here on that stability?
So if you tell me using Hyperledger, there's not enough to answer your question. I would also need to know what kind of consensus mechanism do you use, because Hyperledger is basically just a protocol which you can plug in different consensus algorithms, right? I mean, you could take Bitcoin and plug in a different consensus algorithm the same. So I'm assuming now that this is kind of a BFT type of consensus mechanism. And in BFT protocols, if you look at just type it in Google, you find the first paper, you will see there are a lot of communications necessary between all nodes before reaching one round of consensus. The advantage is that this is deterministic consensus. It's not probabilistic consensus. So in proof of work, if you wait 6 blocks, you are likely that this is not going to change, right? Your consensus is not going to change. In BFT protocols, you know it's not going to change. There's no fork. In a sense, there's no forkability, right? This is the advantage. But the fact that you have so much, probably one of the major drawbacks is latency and communication bandwidth. Yeah.
Okay, thank you. I think there was a question right here.
Hi, Mike Hesse, consultant at PwC Strategy and PhD student at RWTH Aachen University. I have a question that's probably a bit foreshadowing into the future, but I'd like to pick your brain on it. It's because it has been proposed that when you're talking about advancements on the network layer and the hardware layer, and it has been proposed that there might be some threats with regards to some consensus algorithms with the advance of quantum computing, which would, for instance, put proof of work consensus algorithms at risk because there might be the risk of a 51% attack. Now, some of other DLT structures that have been discussed earlier, such as the AGs, are proposing that they are quantum resistant. So is that something? I'm just curious on your thoughts about that. Is that something that could put a threat towards current scalability and security discussions? And how do you think DAGs might be an answer to it or not?
Thanks, great question. Quantum technology might be an issue, not directly to the mining, not directly to proof of work. To do proof of work, you need to do hashing, and a quantum computer is unlikely to be faster in hashing than like a traditional ASIC. So from that point, I don't think we have an issue. Where we do have an issue is with cryptographic signature schemes, and this applies to both permissioned and permissionless blockchains. So if you use a public key cryptography system, and your quantum computer enables you to compute basically back from the public key to the private key, then you can impersonate whoever you want, right? And then you're lost in every setting, basically. So it's a major issue for not only blockchains but also the web. For any HTTPS connection that you have, it's an issue. So it goes much beyond blockchain, but there are fixes. There are signature schemes that are resistant. The major drawback, however, is that they are much more inefficient than the current signature schemes that we have. So basically, blockchain scalability will take a hit as soon as we have publicly confirmed quantum computers that could attack those. Can I steal bitcoins if I have a quantum computer? You can, but it would require, so if you do a transaction, if I'm paying Ludovic, for example, a transaction to his address, and he has never used this address, then nobody can steal his Bitcoin that I just sent him. However, the moment he's using this particular transaction output that he got from me and spend it to someone else, to Chiara, then a quantum attacker could intervene and try to steal it, right? So there are some specific cases that need to match for an adversary to be able to steal funds and to be fast enough. But it's certainly a concern, and it will make scalability just harder.
Okay, thank you very much for all these questions. I see that there was a lot of energy here. Of course, if you have more questions, please ask them during the lunchtime. We will have time for coffee also, so please do so at this moment. Thank you very much, Arthur. Please, a big round of applause for Arthur.